I think we have about 23 people, sizable number. I think we can start. Archana, will you be able to start the session?
Okay, sure. Yeah. So thank you all for joining. I think my voice is audible, right,
Yes.
Nanda?
Yeah. Yes.
Okay. Yeah. Okay. Thank you all for joining. And I think it's a Saturday. I understand there's a lot of people. It's a holiday, and you still are kind of this shows how we are all kind of connected as a social network and trying to learn from each other. So welcome all, and good morning to for all the folks. So let me quickly introduce our speaker for today, who is Lakshmi. So Lakshmi Narsiman, he's a very seasoned engineering leader with over 2 decades of experience building a large-scale platforms across Java system and modern AI-driven technologies. He has held leadership roles at IBM, eBay, Amazon, and Uber. He's working on globally scaled systems which are spanning across search, billing, maps, and platform authentic automations. Currently, he is a director of engineering at Capital One. Lakshmi focuses on building reliable, scalable platforms, while he also enjoys mentoring engineers and exploring practical applications of LLMs and RAG in software engineering. So I welcome you, Lakshmi, and I think there's a great learning every time I kind of join your sessions as well. So before handing over Lakshmi, I'll just quickly introduce Blithe over here. So Blithe, I have Prince from Blithe. So Blithe is basically for people who are new here. It's a dedicated platforms for micro creators and hobby organizers to transition from passion to profession. By automating the logistical burden of coordination, ticketing, and payments, they empower our host to reclaim their creative bandwidth. So, Blith, thanks. Like, would you like to? This is a new platform that we are also trying to learn. Like, anything you want to add as we have more people learning about Blith as well.
Yeah, so in fact, it's called Blythe. I mean, the pronunciation is called as Blythe. So,
Oh,
our small objective of supporting the hobby creators and the organizers. So we have platform, event discovery platform, and some uniqueness. What we have this mood-based event discovery. Like the current mode is like whatever you think about, we'll give you some of the suggestions in the city. And yes, we are just launched. We have started hosting the events, paid events, and ticketing events. Anybody interested to be participate, we just posted our website link and Insta page. Just have a look at that and approach us. Thank you. Thanks for
thanks,
giving this
thanks.
opportunity. Yeah,
Thanks, Prince. Thanks. Apologies, it's Blythe. I learned that something new today. Okay.
no worries.
Okay, no worries. Yeah. So, and then finally, I think this session is hosted by SaaviGen. So, SaaviGen focuses on helping professional and organization build practical AI capability. We work on AI fundamentals, upskilling the teams, and helping enterprise build secure their AI systems and data. So, with this, I think I can hand over to Lakshmi, right, Nanda?
Yeah.
Okay.
Thanks,
All
Archana,
right.
for the introduction.
Thank you. Thanks a lot. So I'm going to share my entire desktop because we will be jumping between multiple screens here and there. So if I'm moving too fast, please do let me know if you want me to slow down. So first of all, thank you, and really appreciate all of you taking time on a Saturday morning to join the session. This is probably the last session in this series of large language models. The next sessions will all be very different. So in the prior sessions, we have been kind of walking through different techniques that one could use to essentially improve their large language model performance per se. And as a sort of the last step in this, today we will talk about one powerful technique, which is called fine tuning, which allows us to uh, essentially convert a generic large language model into something which is very domain specific. And then to add the cherry on the top, we will also kind of say, okay, now that I have fine-tuned this so-called model, how do I kind of compress it so that I can make it really, really small and run it on my phone? So as a demo, we will see if we can push that model onto my phone, and then we will actually see how it looks like. As with most of the demos and most of the sessions, there's a very high chance nothing will work. We'll keep fingers crossed. Okay, all right. We have a lot of things to cover, so let's jump in. Sorry, just give me a second. Let me close my door. Sorry about that. Okay, so we'll do a lot of hands-on today. At least I will do a lot of hands-on today, so that we all actually get to see what's going on behind the scenes. So we will take one sort of well-known large language model, let's say Llama 3, and then we will say, okay, let's ask it a question and see what it responds. And then we'll ask a very similar or the same question to a very tiny model, and then actually see how that model responds. Hopefully, we will be able to see based on the responses that what are the gaps that we can see between a large language model and a small language model. Then we will jump into this process of fine-tuning, which is going to be about how do we actually train a model to become a specialist in a specific area. We probably know so far that there are different techniques. Prompt engineering is one, which is essentially to structure the knowledge that the large language model already has to be able to give the response in a certain way. We also explored in the previous sessions RAG, which is a technique where you ingest context into the existing knowledge of a large language model for it to be able to respond back with responses which are probably more specific to the domain that you are working towards. This session, we will focus on the next step, which is fine-tuning, which is, okay, can I foundationally alter the behavior of the model itself to be able to get better at responding with things? We will spend some time. This is going to be we will see hopefully a lot of code. I told Nanda that we have gradually increased the technical complexity of the sessions. So this session, there's going to be more code. We will walk through what actually the training is doing. And then last but not the least, we will say, okay, now that I have sort of fine-tuned a model, now how do I convert it into a format that allows me to deploy it onto a mobile? And we will push that model into my mobile phone. We will see how things look like so far. Okay. All right. With that, let's move on. So the analogy of a generic model versus fine-tuned model is pretty similar. Like we all know a general doctor, a GP, as we call it most of the times. They know generally about a lot of things. They can diagnose common problems for us. They can give specific medications if need be, etc. Broad knowledge. Sometimes pretty shallow depth on any one area. Compare them to a cardiologist who is somebody who's also a doctor, but they didn't have to relearn all of it. They knew, they kind of know most of the things, but then they went deeper, specializing in a specific area of a body. In this case, the foundation remains the same, but their focus is very specific. But they are fine-tuned for a specific area of a problem. So the base model, which we will probably see, is the generic doctor. They are broad, they are capable, general purpose. The fine-tuned model is a specialist who is fine-tuned to be able to learn from a specific domain. And the technique which we are going to use to actually fine-tune the model is called LoRA. There are many techniques. So today we will talk about LoRA, which is lower rank adaptation. And we'll understand a little bit more about what does LoRA actually do, how is it able to fine-tune the model, what does fine-tuning actually mean, and all of that. Good so far?
Yes.
Awesome. All right. So just again, some concept, what does fine-tuning actually mean? Fine-tuning, we said a pre-trained model already understands grammar, reasoning, context. Fine-tuning does not teach it the elements of it. It basically changes the model's path understanding by adjusting what we call as an internal weight. Don't worry too much about it. We will get into this. Focus now on the last three boxes. What is prompting? Prompting changes what you ask. RAG changes what the model sees. Fine-tuning changes foundationally what the model itself is. So broadly keep that in mind, and then as we go further, we will hopefully make this clearer.
So Lakshmi, is it something that we can say RAG is temporary for that prompt, and fine-tuning something that you change the memory of the LLM itself permanently?
Permanently is a very big word. I'm
Mhm.
just what we are actually doing is when we look at the subsequent slides, we will realize that we are actually not changing the base model.
Mhm.
We are actually adding it, giving it a little bit more additional context in like a RAG. I have a very bad example of it that you see. So think of it like you're able to draw shortcuts to. So you have a way to go from your house to, let's say, your office, and a large language model has the ability to adjust itself every centimeters. That's it. Okay. Now, and then it keeps course correcting itself. Every centimeter, it changes this direction. LoRA and QLoRA and some of the other techniques slightly look at how the base model is responding, and then they adjust the weights to be able to say, okay, rather than doing all of this, just do this one part, just do this one part. Think of it like a shortcut that they're trying to put. We will get into the details a little deeper, but
Okay.
this is not changing the base model. It is not changing the base model, but we are adding a lot more what we call as tensor weights, which then allows the model itself to be very different when it responds back.
Okay.
Now, RAG can be still on top of this. We will come to that. Okay. So what actually happens? Like, to answer your question, what happens? So think of, like, there are multiple dials. So when somebody says there's a 7 billion parameter model or a 24 billion parameter model, it essentially means there are 24 billion dials that exist within the model. Now, large language models are nothing but neural nets. There are many layers of the net. There are modules and components, and they are interconnected with each other. Each of those connections is essentially a parameter. So the higher the parameter, the more fine-tuned the model can be. By that I mean the more nuanced it can be. So each dial influences some aspects of how confidently it does. Then fine-tuning essentially is changes those to see the output that you want. We'll go through this. For now, just understand that it's the process of where you slightly adjust the weights to be able to get the response that the large language model got. Okay. Questions are there? Let me see.
No.
No questions, right?
No
You
questions.
please, another you if you.
Yeah, I'll track.
Okay. All right. So LoRa does basically things like loss calculation to say it makes a change, sees the output, and says how different is this output from what the base model did, and then it adjusted. So neural nets and typically transformer models work with the process of backpropagation, where they're able to pass back the context. So they then LoRa has the ability to essentially walk back the layers to find out where did this error actually originate, and then it builds this prediction, which is called forward pass, to be able to say what is next likely to come, and then it keeps adjusting the weights so that it essentially, without the student model actually having to learn everything based on what the teacher said, that the student just tries to mimic what the teacher said and what's the best way to get to their answers. Okay, so as it says, LoRa doesn't arbitrarily change it. It looks at what is the correct response and then keeps fine-tuning the response till it gets the answers. And then this gets repeated over thousands of data sets. Don't worry, we will actually see how it works, but for now, these are some of the conceptual understandings. So there are many techniques, as I said, when it comes to fine-tuning. So we'll start from full fine-tuning. So model weights, as they call it, the parameters, it essentially full fine-tuning essentially updates all of the layers, all of the weights. Now, this is generally what the GPT 4.0, 5.0 do when they roll out a new model. That's why their training costs are really, really high, because every model or every layer's cost needs to be adjusted, and this is pretty expensive. LoRa, which is what we are going to do, essentially is only the adapter layers. The cost is low to medium. It outputs an adapter file, which can then sit on top of your model to be able to respond back. The risk is low because the base is still preserved, which means the base model is still out there. QLoRa, which is this quantized LoRa, which is essentially the same thing, but it does even further down, which is essentially bringing it out to a 4-bit quantized base, which means that the adapter that it builds is really, really low in terms of the size. Distillation, which is also something that we will look at towards the end, which is it produces a completely new student model, and we'll look at it. So distillation is the process of essentially abstracting out the teacher's knowledge and creating a completely new student model out of it. So generally these are all industry practices. They say start with QLoRa, and then it's generally far more beneficial. And this is what we will also focus on. Okay, what better way than to actually see it in action? Let me just pull up. Some of you who have attended my previous sessions might know that I have this, I use Ollama extensively. Ollama is essentially a tool that allows you to run your language models locally without having to pay for it. So for the sake of experimentation, I keep downloading multiple LLM models and experiment with them. So currently I have all of these models which are downloaded and available with me. And what I'm going to do is I'm going to pick sort of a large language model, which is an 8 billion model, Llama 3 model, and we'll ask it a question. And we will ask the same question to a tiny model, just for you to know that how the models themselves are different. Here is where I'm going to jump into. Sorry, I have a lot of windows open. Let's see, let's pick. Okay, let's pick this question, which is called BERT. What distinguishes BERT from other transformer models? So I'm going to ask this question to Llama 3. This is going to take some time because my laptop is a decent laptop, but not a big enough laptop for it to return this in a sub-second. And if you are interested, we kind of talked about it in the previous session. We can very quickly look at how various large language models respond to the same question. And it kind of shows the personality of them. DeepSeek, for example, is a big time reasoning model. So anyone who has used reasoning models like DeepSeek, a lot of thinking. Llama 3 is a lot more optimized model. So it is optimized for efficiency and faster responses. So it is generally much more faster, but it won't tell you how it arrived at that answer. We looked at Gwen. We looked at a bunch of other things last time. I hope it was a fun exercise. Let's see when it responds back. Okay. So if Subhashish, if you don't mind, we will kind of we will look at the questions towards the end because some might get answered as part of the session itself. So we will keep these questions, and towards the end, if we didn't cover them, then I will try to answer them if I know all the answers. Okay, so this is a great example. You can see that how slow my system itself is, and how much of a compute it actually requires for somebody to run a large language model locally. Let's just give it 1 minute, and I'm sure it will cover.
We can see that there is a small lag in between Lakshmi when you're speaking, as you speak.
Okay, I will be aware of it. So while this probably comes up, why don't we ask this question to ChatGPT just to save time on this? Let's just say GPT 4.0 or 5.0 is also a pretty good inference model. So as you can see, this is so fast. This is fast because they have thousands and GPUs running behind this scene. So now this is what GPT-5, I think, is giving like pretty detailed, pretty elaborate responses. So, okay, so this is still running it. So I don't know how much more time it's going to take. So let me just stop this part of it. Really sorry. Okay. Let me ask this question to Tiny Llama, which is a very small model. Now that we kind of have some sense of how a big language model does, so let's ask it to Tiny Llama, which I'm hoping will answer back pretty quickly. Tiny Llama is, I think, a 1 billion or 2 billion parameter model, very small, and it should be able to respond back very quickly. Just a second. As with demos, always, this is how every time you think something will run, it will not run. Okay. So this is running, but it's running very slow. So I'm just switching back to my command line of it. So I have Olama, I'm running Tiny Llama from my command line prompt, and I'm just going to ask the same question that I pasted over there. What distinguishes this bird from other transformer models? Okay, this is also running really slow. Just okay, it's running it. Okay. So Tiny Llama does a pretty decent job. As you can see that though the responses were not as elaborate as what we saw a GPT-5o doing, it does a basic aspect of it. The tone of it is different. It's more formal. You might see that GPT-5 could be a little bit more conversational in nature. So when you're fine-tuning a model, you can not just infuse knowledge context, but you can also infuse tone context. So while you can influence it by prompt also, by actually fine-tuning your model based on how you want the responses to be, the model will tell it in a tone that you think is appropriate for your organization or for the kind of audience that you're trying to get this model to. So this was just to kind of give you guys a quick peek on the fact that a large language model and so-called small language model work differently, and what could be different in terms of it. So, wow, sorry, I don't know where. Okay, we talked about this. Okay. So we talked about distillations. We talked about some common terminology differences. A lot of people confuse fine-tuning and distillation. Fine-tuning is different. Fine-tuning is basically you're sending somebody for an advanced training on a specific area or a domain. There's a basic skill that already exists, but then you kind of enhance it for a specific domain. Hopefully they come back smarter, and but they're still the same person. Distillation is very different. Distillation is where you take a large language model and then you generate some set of answers. The smaller model tries to mimic those answers. So the student is not necessarily learning the concepts themselves, but they are only trying to understand, okay, what is the shortest way to get to this answer that the teacher said? Now, it is very cheaper to run, but it can carry quality loss because the student has, in some cases, not necessarily learned how the answer came about. Like the square root of 16 is 4, for example, and then square root of 36 is 6. In the case of a fine-tuning, the methodology of how 36 square root is 6 arrived is learned. But in distillation, in many of the cases, the student tries to just find a pattern. Okay, if this, then that, if this, then that, have a view. So it can carry some quality loss, and that's something that to be known of. So from a model size perspective, in the case of fine-tuning, the fine-tuned model remains as big as the base itself. Distillation, the resulting model is smaller. Cost is medium. Distillation is really, really low because we end up getting a very small model. Inference speed is the speed at which it is able to respond back and essentially walk through the layers. Depends on the base size, which is if it's a large parameter model, then it takes time. Distillation generally is much more faster because it has fewer parameters. What is the use case? Use case is when you have to build a domain expertise on a capable model. Like you already have a base model, but now you want to build a very specialized domain expert on a specific area, then you go with fine-tuning. Distillation is great when it has to be deployed on very small contained environments like mobile edge, any of your IoT devices, etc. Then you have to go to distillation. Now, in this session, we will actually do both fine-tuning and distillation. Fine-tuning makes the model special. Distillation essentially compresses the model and gives us a very small model, which we will then push into our mobile and then see whether it has improved any of the performance or not. Good so far?
Yes.
Okay, all right. Now let's jump into LoRA, which is the technique that we are going to use to essentially fine-tune the model. LoRA is essentially an approach. It's called lower rank adaptation, which primarily works on instead of retraining the entire model, think of it like it puts jumpers, which creates clips on top of the layers with learning. Like you freeze the base and then you start putting clippers on top of it to build in some specialized understanding of the existing system. So the base model weights, which is basically the 8 billion parameters that I said, that's frozen. That's not changed at all. LoRA essentially listens to the responses and then tries to build training layers on top of it, which is essentially adds. We'll talk about it later. Net, what LoRA tries to do is, hey, instead of me having to touch every single parameter in this model, can I achieve a specialized knowledge, specific response just by fine-tuning some smaller parameters of it, which is, in this case, it says 0.1%, but it depends. But the net result for you is just the base model remains the same. You just come up with these set of adapters, which are now being fine-tuned for the domain that you want the model to perform with. Now, what it actually does is that, now this is a little bit of math, but if you have a large language model in 8 billion parameters, depending on the number of layers that you have, it's an n cross m matrix. So this is a matrix weight. Now, LoRA first freezes that is a base model's matrix weight. And then as a question is passed to the base model, it essentially changes the adaptation, which is it keeps creating a new layer on top of it to adjust the weights. Towards the right, you see this orange box. Now, a full weight matrix could be a large one with 16 million values. LoRA essentially tries to come up with this delta value, which splits it into two matrix, one length 4096 into 8 matrix and a breadth which is 4096. So instead of having to update and look at every parameter within this large matrix space, it tries to come up with a smaller matrix which is fine-tuned to get the response. Basically, it comes up with an adapter that says, okay, there are these 65K parameters in this case as an example, which it adapts and changes the weights to say that, okay, when these weights are modified, the base model will respond, or the newer model that I have will actually respond back with the answer that the base model gives. So in this case, it does it by reducing the number of paths that needs to be traversed to get to an answer, to very frankly put. Now, this is the outcome of it is essentially this this parameter inference space that it generates. Now, when the actual inference happens, the newer model is loaded. This is loaded on top of it, and then the answer comes up. we will try and see towards the subsequent slides how some of this might actually look like. Okay. Okay, all right. So I think we talked a little bit about this. I kind of jumped it. So this was the demo question was supposed to be like we take one question, we ask it to a large language model, and then we ask it to a smaller model. Like this question was basically chosen for some sort of an architecture thing, but I then prepared a set of about 250 questions, etc. So I picked one from it. But largely you were able to see the difference that a model with a larger parameter is a little bit generally more precise, more verbose in a lot of cases also. It's able to kind of give a lot of cases. Fine-tuned models, not smaller models, are very generic and surface level. They give some sort of a correct information, but can miss some reasoning concepts and stuff like that, etc. And this is what we will try to see if we can bridge by building fine-tuning. Okay. Now, here is what we are going to do through this session. So we are going to build, or we are going to run through a pipeline that I had created, which essentially takes a set of a data set. Now, fine-tuning means you're going to fine-tune something based off something. So for the sake of today's talk, I had generated a set of about 300 odd questions, and then I had asked each of this question to a large language model, like an 8 billion parameter model, Llama 3, etc. So that data set and the question and responses were generated. Now I am going to basically run it against a different model. Okay, I'm going to use LoRA to fine-tune this newer model based on the responses that I got from the other model. And then LoRA is going to produce a set of adapters for me. Now, with those adapters, now when I ask the question to the newer model, it hopefully should be able to respond back with a better answer. And then we will take this, I don't know whether the right word is student model. I'll still go with student model. I'll take this student model and then we will compress it and we will make it really small and then we will run it. So we'll do fine tuning first and then we will do distillation next. Any questions so far? Okay. Okay, so yeah, we will use LoRA, and then we will generate training examples from a larger teacher training model, and then we will save the adapters. Let me just quickly go ahead and see. Okay, so because fine-tuning is about adding more expertise to an already existing model, you need to give it some data to say, what is this expertise about? It could be domain-specific expertise, or it could be a language-specific expertise. So in this case, for example, I have come up with some set of 250 odd questions. Let me pull that up somewhere here. Okay. My screen visible?
Yes.
So I had generated from about 30 topics of computer science, design, and architecture. I had generated some set of questions. And then, like for example, what is Turing test? And what does it signify for artificial intelligence? And then this question was sent to GPT-5. And then GPT-5 came back and gave this response. It says Turing test is a measure of machine's ability to exhibit intelligent behavior, blah, 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 blah. So like this, I had about 250 questions covering software development, testing, artificial intelligence, a bunch of different criteria that were where I had essentially asked it a question and kind of got the responses back from GPT-5. Now, this is stored in a file which is called the teacher dataset. Now, this teacher dataset JSON contains these 250 question and answers that I have received from GPT-5. Now, I'm going to take these questions and I'm going to train another model, fine-tune another model using LoRA to say, okay, you might be giving me some answers, but now look at what the teacher is told as the question and answers, and now you fine-tune yourself. Now LoRA is hopefully going to produce us some sort of an adapters, which but then say how the responses will have to be built to be able to match with what the student said. Sorry, the teacher said. Okay, so that is the goal of fine tuning. And then, sorry, I'm just jumping back between here and there just so that we keep it in sync with a flow. So the teacher model, we generate some question answers pairs, and then we that gets generated into this JSON file, which I just showed. And then we will basically fine tune another model from these teachers' inputs. Question, yeah, why did I write the code? Because you could handcraft these question and answers also. And how a teacher model can generate all of these questions and responses very quickly. And you can also have edge cases. You have to obviously make sure that the teacher model itself does not become factually incorrect. It does not hallucinate. Again, some of you who attended the last session will know that there are a couple of parameters that you can use to control the hallucination rate of your model. Temperature is the one. So keeping a very low temperature forces the model to be more grounded to reality than come up with its own weird answers. And then remove duplicates, validate the request responses, etc. And as with general things, high quality database, high quality data set is very important. Even if it's small, if it's good quality, then it's guaranteed to produce a better response than a noisy larger one. Okay. So I said we talked about it. We talked about how we generated this JSON, etc. All right. Okay. Now we are going to actually start the fine-tuning part of it. Let's see. Is my screen visible?
Yes, Lakshmi.
All right. Yeah.
Could you please increase the font a little bit? Yeah, a little bit. Thanks.
Okay, this code, I will request Nanda to put it up somewhere so that it's out there for you guys to clone and use it. Just give me 1 second.
Sure. So until Lakshmi fix it, no, I've shared the WhatsApp group. Please see if you can join there. We will have this recording on the YouTube channel as well as on the WhatsApp group.
Okay, all right. So there's a larger file called fine-tune llama 2 that I had generated some time ago. So which is what I'm going to actually use to actually do the fine-tuning part of it. Great. This is pretty interesting. Sorry, guys. So because fine-tuning typically takes a lot of time, so I had to rent out a GPU space to actually run this. Okay, great. It's not working. Let's jump to my laptop. I know here it works. So what we are going to do is we have the teacher dataset generated. Now we are going to take the teacher dataset and then we are going to fine tune our model. The teacher dataset, you could have generated it from any language model that you have. It could be, for example, you could have put it into Perplexity and then you have got it at Grok. It doesn't really matter as long as you have as long as you know that the model is decent enough, then you can use that model to generate a request and response, and then you get answer. Okay, great. Sorry, guys. Just give me 1 minute. This did not happen till today morning, and I'm sure sorry. So I'm just going to reconnect to this box. Okay, sorry about it. I don't know what went wrong. Sometimes because I'm just installing multiple toolings at one environment, I have seen this issue happen. Let's see. Okay, so I now know what happened. I had installed a different version of a library for testing something else, and then it's now crapping out with this error. Okay, but I'll kind of walk you through what actually happens, and then I have the outputs of it, and then we will take those outputs, and then we will run the question against on them, and then see if it's able to produce a better answer, and then we will talk about quantization. Okay, so
I'll mute
all right,
it.
okay, no problem. So at the core of it, what fine-tuning is trying to do is basically it loads the base model, and then it the questions that we had about 250 questions that we had prepared. So it basically asks those questions to the student model. For the sake of simplicity, I just call it as a student model. The teacher model response has already been stored. It loads the student model, the model that we are wanting to fine tune, and then it asks the question. So now for when the question gets the response gets generated, it basically compares the response with the teacher's response for it. Now, as a human, we might say, hey, okay, the student model is responding differently, but LoRa essentially can look at the adapter weights, like the matrices themselves in CC, and then it iteratively keeps changing those parameters to be able to see it knows which layer of the response is this, which layer of the student model is this response differing from, and then it tries to work out to adjust the weightage at that layer. And then it basically reruns the query again, the question, and then see what is the response that it's getting now. And it keeps doing this iteratively till it gets to a state where the response of the student model essentially matches the response of the teacher model. So, and then it basically says, okay, now this is the adapter. At this layer, I have to change these gauges to get that response. Then it moves on to the next one, then it moves on to the next one. So similarly, at the end of it, it would have run through whatever questions that we had generated and stored as a response. And then it would have adjusted the weights of it to come up with an adapter file, which then says, here is how I have to change the parameter weights to be able to meet the response of what the teacher model had given. What is given over here is essentially some of the technical details around how these gradients are checkpointed. So what the net for it is essentially that we are able to use LoRa to train a model with slightly lesser compute resources than what might be required for you to have trained Llama 3 itself. Llama 3 is an 8 billion parameter model. For you to train an 8 billion parameter model, you require much larger GPU space and memory space. But LoRa essentially allows you to run a very similar thing on a smaller consumer GPU or a single CPU itself. Let me get that to work.
Hey, Lakshmi, you're there?
LoRa keeps creating on top of the model layers. And then it keeps changing it depending on how it sees the response coming in from the model itself. So there are multiple parameters that it uses to control or generate these matrix sensors. One is called a rank, which is probably something that you will typically see most often being used. So you remember I told about 4096 into 4096 gets changed into 4096 by 8 and then 4096 by 8. 8 is essentially the rank order. Now, generally larger the rank order, better the fine-tuning itself is, but it also means additional cost. So higher rank means you need higher capacity, even for training part of it. So generally, in this case, we started with a rank of 8. Next is alpha. Alpha essentially is about, okay, I changed something, and then it's a way of knowing when I changed it, what was the correlation between the change that I did at this adapter layer to the output. It's a way for it to essentially reinforce its learning to see, should I go through a very steep influence curve to say when I change it, the outcome has to be really changed. Generally, it is set as double the size of rank per se. I don't know why, but start with that. Dropout. So during training, when you have very small data set, what ends up happening is that the fine-tuning will force fit the response to do exactly what the data set gave you. Now, while it might be useful for that training purpose, this is typically what many of you might know is overfitting, where you are squeezing the model to behave based on a very small sample set, which may or may not be really valid in a real world. So now this, by setting a dropout value, you are essentially forcing the adapter to recompute those trainings. That is a notion behind dropout that is generally set to prevent the overfitting problem. Okay, now a large language model, which is a neural net, has different layers of it. Okay, now each of these layers do very different things. I think when we looked about some of the in the earlier sessions, we talked about how different LLMs operate at different layers of the model itself. A 1 billion parameter model, which layer of the neural net does it actually work? Whereas a DeepSeek, how it essentially is able to propagate through deeper layers of the network. General principle is more the layers it traverses, the more refined or more reasoning it has. Now, because different layers perform different actions within an inference itself, you need to know at which layer should this adapter be attached to. And that's what is defined by what is called as a target module. So there are different types of layers themselves, as QV, KO. I don't know the details of it myself. But you can start with query and value parameters first, and then fine tune it if that's not really helping you. So the last step in this whole training is essentially gets the response, finds out the loss. Loss is the divergence between the response that was received and the response that the base model has. And then how do you adapt your back propagators so that it basically goes back and changes the weights of it, and then it goes through this loop again. So the whole goal here is that you update less than or about 0.1% of the overall parameters, which is basically the adapter's weight. So the base just remains the same. Your overall memory that is needed for fine-tuning compared to a full fine-tuning is much, much more reduced because you're operating at a very small layer of it. Okay, let's say we do this fine-tuning. I hope I can probably show you what happened after the fine-tuning. Let's see. At the end of the fine-tuning, what happens? The base model remains the same. We have not touched it at all. Now the base model is shared across every instance of fine-tune that you're running. Now you have a newer adapter that got created. Now this is typically, think of it like a n cross n matrix, which we saw, which is very small. And at inference, what happens is the adapter merges with the base model in memory when you're loading it, which is to say that think of it like a superimposition of data, which then guides the responsiveness. Now, why this approach is generally very powerful is because you can have the same base model, but you can now produce very different domain-specific variants of it. So let's say you're trying to build an app for diagnosing some medical issues, like the very same example that we started up with. Now, you can take one base good reasoning model, let's say DeepSeek, if you want to go with it. Now you can start building different variants of it. One which is specifically fine-tuned for this purpose, let's say cardiology, one for neurology, nephrology, urology. So now what you can do is like these adapters are different, but the base model remains the same. So depending on which type of question comes in, you can actually load that adapter on top of the base model to derive an inference. Now this, as a system, if you're building it, saves you a lot of compute and infrastructure because your base model remains only the same. You're only changing the adapters based on the domain for which the response needs to be generated. Okay. All right. Now to the real proof of the pudding. I don't know whether this will work because as you saw, I really messed up something on my thing today morning. I know what I was trying to do and I regret that I did it. But now by asking the same question to the fine-tuned model, it hopefully should be able to give us a better response. Let's keep our fingers crossed and see whether it will work this time. I have a very bad doubt that it may not, but let's just give it a shot. Just give me a second. I'm just trying to. I had copy pasted all of these commands so that I know I don't have to jump it here. Okay, I think I have something which is here. I need another GF. And what was the question that we had asked then? Let's see if we can have. So I had trained a tiny llama model some time ago with some of this tunings. I really wish I can. It'll probably take me 10-15 minutes. I have to just kill that whole instance and restart this whole stuff, etc. So, okay, what did I do wrong here? Is a question. Okay. The question itself was wrong. So now you can see that the answer that came out was very different than what Tiny Llama had said before. So if you look at the original response, so now this is what Tiny Llama had originally said. Tiny Llama had asked what distinguishes BERT from other transformer models. BERT it says BERT is a transformer model for design bilingual text analysis. Some of the key differences, encoder, decoder. BERT is designed to be a general purpose transformer models, blah, 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 blah. Now, with fine tuning, it says that the question is what distinguishes BERT from other transformer models? Now, you can see that the answer is a little bit more pointed. It says it stands out in terms of its beam search, which allows for extended search space for generating output tokens. Sorry about it. So now while the answer is short and terse, we can actually now see that the answer is far more closely aligned with what was the question asked. So here the question is what distinguishes. Okay. Now the answer here is a general transformer model, key differences. It says about differences, and then it says BERT is designed to be a general purpose transformer model. So it is not giving us, hey, what is distinguishing it from other transformer models? It's not, the question was not about why is BERT superior. But with after fine tuning, you can see that the response is very specifically tuned towards the question. Now, if we go back to the questions themselves, let's see if I can find it here. Let's open the, okay, what distinguishes BERT from other transformer models? Sorry, let's just zoom it up a little. So this was the question, right? Okay. This is, the question was what distinguishes BERT from other transformer models? And when this was asked to GPT-5, which is how this response was generated. This response, what you see over here, came from GPT. It said BERT distinguishes itself from other transformer models by using a bidirectional training approach, allowing a model to consider context from both left and the right side of a word simultaneously. So it was a very specific and a precise answer. Now, this answer was partly generated because I had told GPT, come up with a concise answer. Now you can see that Tiny Llama, from coming up with this sort of a response, is able to generate a very specific response based on what LoRA generated as adapter slates. It figured out that, okay, the teacher said this is probably how the answers should look like. Here are the weights that I need to adapt and change. So the response that I'm giving actually closely mimics or matches to what the teacher asked for. So this is hopefully was clear in terms of how fine-tuning alters the behavior of how a model itself works. Is that clear? Any questions on this? This is important.
Getting clear, Lakshmi.
Okay, all right.
Anyone else has any questions regarding this? Apart from the one which is generic, which will take it at the end of the session. I think we can continue, Lakshmi.
Okay, all right, sorry. Okay, so where did we go here? Why have been jumping very badly between? So we talked about LoRA. We talked about this. We covered this. We actually covered this. Now this is where we are, right? Okay, so we basically are hopefully now saw that, okay, the fine-tuning actually produces a response which is more directed towards how the teacher's response itself was. The question that I asked there was different, which is why what you see on the slide is slightly different. But you can see that an adapter file trained for some time over specific domain, specific examples, changes how the model itself responds. Okay, now that we have done fine tuning, now the last step, and this is quantization, which is, okay, how do I now compress this whole model into a much smaller one such that I can actually push it into my phone and actually get it to work. So quantization is very simply put, how do I reduce the number of space that I need to store a particular value, very dumbly put. So instead of going with precise the 16 or 32-bit float values, can I store it in shorter 8 or 4-bit integers to have the value stored? So this is, so if the full precision weight, which is essentially the model weights, as we call it, within 8 billion parameters, think of it like there are 8 billion such weighted scores that are present in there. Now, quantization essentially compresses this into a smaller number, 0.7394, blah, 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 converts it into 0.74, which is an approximation value, but it is, now you require much smaller space to store. A very bad example for analogy for this is also the same thing. If a large language model measures its distance in centimeters, let's say for it to go from your house to your office, it can measure it every centimeters. The dial example that I gave in the beginning, quantization says, okay, I don't have to measure it at every centimeters. I'm going to keep it at a meter level. Now, the advantage of it is you require far fewer steps to store the same value of how do you go from your home. Now, the disadvantage is loss. If it's an exact precise tuning that has to be done at a specific area, quantization might end up giving a loss for you. So it may not be exactly fine-tuned in terms of the maneuvering part of it, but the trade-off is that it's now is a much smaller data that you have to store. So for this example, we are going to take a FE16 model, which is storing everything as a 16-bit, which is about 16 GB in overall size, and then we'll apply a quantization and we'll convert it into a 4-bit model, which is about 4 GB in size, and then we will push it into the phone and then see this. Okay, all right. So this is all right. So let's jump into the actual part of it. So for the sake of running it on my phone and demoing it, I have a OnePlus phone, and OnePlus gives this thing called OneCast, which is essentially allows me to cast my phone screen, which is what I have over here. Thank you. See, now you can actually see that I'm running it on my phone, right? Oh shit. You can see all my WhatsApp messages. So I'm not mimicking it. All right. So is my screen visible? Let me increase the.
Yes, Lakshmi, we can see your mobile in the screen.
Is whatever I'm typing there, is it?
No, we see llama.cpp. That's clear.
Okay, I'll keep it in landscape mode. Okay, so for me to do this, it was only a question of okay. When okay, let's just step back a little. Basic concepts. When we ask ChatGPT, Perplexity, Grok, or anything, what is actually happening is what we call as an inference. Okay. Now, inference is essentially an outcome of all the training and everything that has happened. So what you see is essentially an inference model. To do the actual training, you need the entire model weights and everything, etc. So to train, you cannot use an inference model to train. Inference model is already a refined version of it. Think of it like inference model is the sambar that's already being made. Now, training is when you take all the ingredients that are needed to make the sambar, and then you are changing their proportions and everything, and you're arriving at it. So an inference model can only be run or only be eaten. It cannot be gone back and changed into some parameters. So the process of converting a trained model into an inference model requires a tool called Llama, not OLama, Llama. There are many other things that are available, which essentially converts your model into a form which can now be run as an inference model on any system that you have. So what I have done is I have basically converted it into this smaller inference model. The steps I'll probably show you right after this. It's a very simple command line which can take your learned model adapters and then convert it into a GGUF file, and then you apply quantization to say, okay, don't store anything as 16 or 32-bit, downsize them to be stored as a 4-bit numbers, etc. And then you end up getting a GGUF file. I'll show you the GGUF file also, just so that you know what the size of it is. And I'm actually running the GGUF file over here. So what was the question that we asked there? Okay, great. Is this thing? Let's just go back to the question itself. What distinguishes BERT from other transformer models? Let's see. What distinguishes BERT? So now, this is really crap. What you can see over here, okay, I'll probably then transfer the model that got trained into this. Okay, this I had transferred it some time ago and I had tuned it for something else. But what I will then do is, okay, let's just go to my laptop. Okay, so I have the Tiny Llama GGUF over here. So I need to take this and copy it into my mobile phone. It's currently in my work area. So if I go over here and then files, okay, transfer history, clear all history, clear all. Let me just check. Where did I put it here? Sorry guys, just give me 1 minute. Let's see. I'll put it into the downloads folder just so that it's, yeah. Okay. So the tiny llama.gguf is actually the file that we're interested in. Okay. Now you can see that this is about 2 GB in size. Now this is what I need to transfer it into my mobile. Let's say I think I have to go to import files. And then I have to transfer that file from my okay, now let's do this one. Okay. So after I kind of transfer it over here, I'll be able to run, let this transfer take some time. We'll come back here very quickly. So you transfer the file to your device, any other approaches, then you can run it. Just for the sake of demo, I'm using llama.cpp, but you can build a mobile wrapper on top of it if you want and obfuscate it as an app itself. So you basically have your chat application, etc. The advantage is you don't need anything else to run this on your phone, etc. So as I said, the process of training and process of inference is very different. Training requires you to have the entire model weights and everything available. So a lot of people might see a thing called Hugging Face. Hugging Face allows these models to be hosted. So if you want to really train a model, so you have to go to Hugging Face and download that model. You cannot take an already inference model and then run it on for training. Okay, so that's one thing. And then let's just see, you have merging it, then you basically have converting it, we'll do that. And then you basically do the quantization, which is essentially converting it into a much smaller So the whole process, what we start today is like there was a teacher model which is GPT-4 or 5, and then you had the synthetic data set which we passed on it, and then we used the base model to learn from it, and then we used fine-tuning to generate the adapter layers of it, and then we created the merged model, and then it gets converted into a GGUF, and then you then quantize it, which is basically reduce the size of it, and then you push it into your mobile for it to do the inference. Okay. Blah, 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 blah. General context is prompting is the simplest way for you to get started. And RAG is if you want to add, if there are facts that it did not know or it is likely to change very often, then put them as a RAG. They get pulled in only dynamically. So LoRA is for when you have to do specialization, where you want the model itself to think differently, use LoRA. Then distillation is when you have to essentially compress the model and push it into some place. Okay, that brings us to the end of it. I'm really sorry. This is the issue with changing things at the last minute. I apologize. I'll try and record it and push it out as a demo somewhere so that you guys can actually look at it how it's done. Let's go back. Let's look at the questions. Based on some practical experience, it seems fine-tuning does not teach new facts as well. It mostly changes how the model talks, not what it knows exactly. If you want to ensure that the model is taught with new facts, RAG is still the best approach. Is my understanding right? Yes, we'll put it this way. If there's a knowledge that needs to be ingested into the model at runtime, then RAG is probably the best way to do that. Fine-tuning is there is a base understanding, but now you want to build a specialized skill on top of it. Yes and no. I'll change it slightly. I'll contradict myself over there. The analogy of a general practitioner as a cardiologist is a very clear example of it. Now, the base knowledge is still the same, but there is a domain-specific knowledge which is very different from the base knowledge. Now, the question for you is, hey, is this a better option for me to fine-tune my model, or should I just put it as a RAG? Now, if, for example, a cardiologist's way of investigating something itself is very different, not just the knowledge aspect of it, then RAG will not help you with it. RAG is really, really great, fantastic when there is information which is very domain specific, which is likely to change more often. Like, for example, a customer support sort of use case is a classic example, right? Now, there is a generic customer support service, but let's say for your system, you have a very specific methodology of how you want your customer support agents to analyze a problem, how to come up with a use case, how to debug a customer issue, how to respond back, etc. This is fine-tuning. This is not just prompt, because that knowledge does not exist. Now, newer SOPs or runbooks might keep evolving. That is a RAG. So you fine-tune the model to behave in a certain way. You augment it with newer information which may not be available at the time of training via RAG continuously, so that the model is now equipped to learn to respond in a certain way, has the knowledge of your company's ethos, let's say, but just uses a RAG to augment with, hey, what is the latest? Is there an updated information of how, let's say, a customer calls up and then says, my credit card has been declined. Now, if there's a newer way to respond to this, it's better to store it as a RAG, because that information is more dynamic. But the base knowledge of how I need to react or how I need to respond back to a complaint itself is part of fine-tuning. Okay. Any other questions? I know we are over time. Yeah, code repo link. Nanda, you will put it up somewhere as part of your.
Sure. I think we'll share it both on both YouTube as well as on the WhatsApp that I've shared. Please join in the WhatsApp, or you can find it on the YouTube link once we upload this.
I'll also try and put a demo out there. I'm sure. I am sorry. It is my bad that.
So Lakshmi,
I shouldn't have done that.
someone has a question. Yeah, please go ahead.
Hi Lakshmi, I have one question. So I'm facing one problem, like when say I have something called as scoring. Say I give some input, I creating some artifacts. I need to score it out of 100. Okay, I do have a rack where I provide my knowledge base or save my knowledge base over there. And through GPT, I'm like we are ingesting the rack document, rack data, and with the prompting, right? So every time we generate the scoring, right? So it is not static. And there's a huge difference, like out of 100, like if one time it says 80, next time 85, sometimes 77, something like that. So how can we make such a way that it should return a proper scoring every time instead of huge difference?
So do you have okay, it's a short answer is I don't know. I have to understand this case a little bit more deeper to be able to say that sometimes what people use is what we call as a domain of experts way, which is you send it to multiple experts and then you get an answer from each of them, and then you come up with a statistical way of either doing a mean of it, etc. The second way to do it is, do you have a gradient for you to say what is the range for it?
I'll put in the simple example. Say I have a resume bot where it scores the resumes out of 100. Okay. So for the same resume and for the same prompt, every time it is giving a different scoring. So how to
did you adjust the temperature of it?
Yes,
Like
yes.
Okay. Which model is this?
So we directly use a GPT tokens only. So directly we.
Okay.
This is Shubhashish. We had not exactly the same, but a similar incidents in our program. How we adjusted is to using a technology architecture. It's called self-consistency. There is a book, research paper also on that. Very simple term. What it does is that it will generate the different results. The moment you are calling with different times, it will generate. You cannot control with your inference model. So what we are doing, parallelly, we are calling before returning the results three times, the same inference, same endpoints. And then we are taking and we are doing and voting, and we are returning the highest voted. So if out of three times, two times is generate X and one times is generate Y, so X is my response that to be shared with the users. It's broadly in a very simple term, it's what we are doing. Probably this is something you can also adapt. Just wanted to share.
Yeah, thank you, Shubhasish. So you will be taking the average.
Not the average, it's the voting. So
okay.
yeah. You read, there are many content on self-consistency over the internet, so you will find it out. So
Okay. Yeah, sure. Thank you.
Thank you. Thanks a lot. I have very little knowledge. I know very little of what is in this space. So this is a great space to share these techniques and find from each other what works.
So Lakshmi, can you give us one or two examples of running small language model?
Use cases, you mean?
Use cases. Yeah.
Oh, I mean, absolutely right. Like the imagination is something. Alexa is a classic example. Okay, so you can build a simple voice recognition model to run on your local LLMs. Now, personal assistants. Now, with OpenClaw and all of those things, if you have an inference model that can be run on a very small device. It could be your phone, or it could be a clip that you can put onto it. It can actually connect to devices. It could connect to your phone. It could connect to other devices to be able to talk and infer what you're saying and respond back. That's a use case. SLMs are also typically used for IoT devices, edge devices, CCTVs, drones, for example. So a lot of these models require some sort of neural nets, like drones, for example. When they are flying, can they map a pattern of a terrain? They typically use CNNs, but with BERT and some of the other visual models, which can now be quantized, you can do intruder detection, for example. Hey, somebody. So the use cases are like infinite. Self-driving robots, self-driving cars. So there are many different things that can be put onto small quantized models.
So you're basically saying like bringing the intelligence to the edge, closer to the where the action happens. Previously, we used to do that decision on the cloud.
Yeah, exactly, right. Like you have to, they were only primarily acting as sensors, and then you would push the data to a large system, which would then do all the inference for you and then push it back into the edge for it to respond. But in areas where there is little or very poor internet connectivity, for example,
right,
then you can actually use LLMs. Now, the use case we talked about our mobile phones is very different. Like everything, instead of voice assistants, translation, you can have your personal assistant doing things. You can, for example, they can run on smaller computers also, right? So any task that today requires something to be sent to a central server and then got back is all can be voice control interfaces is an example. Diagnostics could be an example. So I
think
use cases are infinite.
Imagination the only limitation.
Yeah.
Thanks, Lakshmi. Anyone else has any questions to Lakshmi? All right. Thanks, Lakshmi, for a wonderful session. I think this I probably lost the count as, I don't know, fourth or fifth session in the last couple of months. Everything is like deep dive sessions. I'm sure we will continue to have these sessions. Thanks, everyone. Post this session, give us some time. We will upload this recording as well as more time for Lakshmi to see if we can get the demo also to be uploaded.
Yeah, I'll fix it. Yeah, I'll definitely fix it. I'll record it as an MP4 and I'll put it into the same GitHub repository with the steps. Okay,
Yeah.
what all you need to do and how you need to do that. Okay,
cool. Okay, and I think Lakshmi also shared some GitHub repository.
Yes.
See if you can join this WhatsApp group for upcoming sessions, as well as any demo code repo we'll be sharing on the WhatsApp group. Thanks, everyone. Have a wonderful weekend. Thanks, Lakshmi.
Thank you, guys.
Thank you.
Thank you, man.
Thank you, Lakshmi.
Thank you.
Thank you. Okay.